Thank you, and welcome everyone to this session on Postgres at scale. And first of all, thank you to everyone who's basically stayed back for this final session. By this point, you actually have two kinds of people that are basically, one is you're heading for the exit, and the other ones are basically that really love the databases. So I'm glad that we actually have the second group in here. So today, as mentioned, we'll actually be sharing some of the hard-earned lessons on running multi-terabyte clusters of Postgres in production. We'll also cover some of the real-world challenges that we've seen with some of our customers and some of the practical solutions and architectural patterns that we've seen work at scale. But first, I'm Roneel Kumar. I'm a Senior Database Specialist Solutions Architect at AWS, and I'm based out of Sydney, Australia.
And I'm Sameer Kumar. I'm a database specialist as part of Enterprise Support Org in AWS. I'm based out of Singapore. Now, here's what we are going to cover today. We'll start by talking about some of those fundamental differences that start surfacing as you start going into the terabyte territory from a gigabyte scale database. These are things that you don't expect to break at a gigabyte scale, but they are fundamentally very different the moment you start working with multi-terabyte databases. We'll cover some critical areas that you need to plan about, that you need to be cautious about, caveats, as you go into terabyte scale databases. And we'll cover some critical talking points or things that you need to keep in mind when working with storage planning or when thinking about the favorite topic of everybody in the room, vacuum, or replication, and the admin task like schema changes and such things. So, Roneel, what actually changes the moment you go into a terabyte scale from a gigabyte scale?
Well, everything, mate. So we've actually been, so example, we've been running a like Postgres cluster, say at 100 gigs, or say maybe 500 gigs, and everything works, right? So we actually have got, queries are running fast enough, backups are taking 10, 15, 20 minutes, and life is good, right? And then we basically cross into the terabyte territory, and it all changes, right? Maintenance windows, start taking days instead of hours. We've got basically missing indexes that could actually bring down the application, instead of just having general slowness in the database. So, and on the other front, we'll basically have things like backups that finish just hours before the next run of the backup schedule, right? So the penalty also of running things like OLTP queries on an OLTP system is, more than just a performance degradation.
So it's not just about handling that large scale of data or having a massive storage. It is completely rethinking how you operate. It's a different operating model altogether.
Well, exactly, mate. So every assumption needs kind of to be re-examined here.
Okay, let's start by talking about the easiest thing in Postgres, getting the vacuum right. Yes, everybody in the room agrees is the easiest thing to deal with in Postgres. Well, I have worked with a lot of database administrators and DB engineers who, after migrating from a commercial database, they think about vacuum as some sort of evil in the very early days. And in fact, I've been in discussions with customers where the database engineering team will first come and say, hey, we have heard really bad things about vacuum in Postgres. We have heard really bad things. It's really bad in Postgres, right? So, Roneel, can there be a world without vacuum in Postgres?
So, as we all know in the room, vacuum that's something that's not optional. But for argument's sake, and to amuse you, let's actually paint the picture of a world without vacuum, right? You'll actually have, day one, you'll start with everything that's running well, right? And then in a few days, you start noticing slowness in the database. Your table growth doesn't align with your actual production workloads. And then in a few weeks, nothing starts to make sense. You start getting, these wraparound warnings in your Postgres logs and in your queries. And then basically databases, the database basically just crumbles to a halt. Now, okay, we've actually established kind of like that vacuum is necessary. So let's see how it's handled, and the handling of auto vacuum, and where it needs kind of a little nudge from you to actually work better.
Yeah, right. Well, the auto vacuum settings, they are really good for tens of thousands of rows, or even as you go to hundreds of thousands of rows. Those triggers or those thresholds, they don't really work as you go into millions of rows. And what you need to do is lower those thresholds so that vacuum can get triggered more often instead of having to wait for 500,000 rows change or a million rows that have changed, and only after that vacuum can get triggered. It's like cleaning up your house or the hotel. If your room is getting cleaned up every day, you are having a very little overhead of having to do the cleanup. But imagine you don't do the cleanup for almost a quarter, then you are probably going to spend up that Sunday afternoon doing the whole cleanup. And that very similar analogy applies to the cleanup in case of dead tuples in Postgres as well. So you want to do vacuum more often so that it gets triggered on those large tables more frequently.
So basically we're saying, set, scale factor for the larger tables. What about things like auto vacuum workers and cost limits?
Right, so you basically want to increase the auto vacuum workers when you have few busy tables. The default is 3, which is not good enough if, let's say, you have 20, 30 very busy tables, because they are always going to queue up. Especially the larger tables will typically get queued up behind the smaller tables, depending on when their luck turns out. I'm saying luck, but there is this whole algorithm behind it. From a DBA perspective, it seems like it's some tables are getting lucky. Now, this is where you can have more workers, and that will help you make sure that vacuum is able to keep up with your workload. Then the next thing you want to do is tune the cost limit. Otherwise, vacuum is going to tiptoe around a very busy room and not try to clean up, and so that people don't get disturbed. But that kind of defeats the purpose. So you want to increase the limit, especially when you have large tables, so that vacuum can finish cleaning up those dead tuples. The thing that I can think about is, manual vacuum. So schedule off-peak hours manual vacuum so that it can go full throttle and do the cleanup maybe once a week, once a day, depending on how busy is your workload. Now, let's see an example of how some of those assumptions of 100,000 rows start breaking down when you have a million or a billion records.
Yeah, so if you actually see we actually have our performance insights metrics, but this is basically your database metrics on weights that you can go in and see. And we basically see kind of like 3 phases in here. On the left-hand side, or the leftmost, you kind of have the database basically running with the default settings, let's say, and we actually have bloat that's actually growing. We've actually got buffer mapping weight types that are climbing. And in the middle, we see per table statistics, or per table thresholds rather, that basically get deployed for the larger table. And on the right, vacuum starts to catch up, starts to do its thing, and our weight starts to drop. CPU kind of becomes our dominant color and the dominant weight type in here, and this kind of becomes like this is a sign of a healthy cluster, right?
Yeah, one more thing that I would like to add there is you need to monitor vacuum progress. So there is PGstat progress vacuum. That will give you what the vacuum is doing right now, and as vacuum goes through different phases, all of them will appear in that view. And you can also see if there is a scan going on, how much of that scan is completed. So you will know ahead of time if the vacuum is getting stuck, and before your end users notice a problem, you will be able to be on top of that and mitigate that problem. Now, I think, Roneel, you have got one more story there, so let's get to that story.
Yeah, so this is also a real story. So we actually had a customer with a very large Postgres database, and the DBA basically got paged at 3 a.m. with a message, your database is slow, queries are starting to time out, and users can't log into the database, the usual panic. And the first thing we kind of checked was PGstat user tables, and there it was, right? Basically, we actually had a table with a 8 terabyte table with roughly about 40% bloat, and if you actually do the math, it roughly equates to about 3.2 terabytes of dirt tuples just sitting there. And every query that was running was basically wading through it.
Where was autovacuum all this while?
So it was running, and it had actually been running for a few hours. As you can imagine, on an 8 terabyte table, a single autovacuum worker is trying to scan through the entire thing. And it'll actually go through and scan things sequentially as well. It is trying to actually, basically think of it trying to clean a football field with a broom, right? So, it's actually going to take forever to actually complete. So with that, Samir, should we actually approach another situation, mate?
Let's talk about this one first. So, do you want me to talk about how we got out of this particular situation?
Yep.
Yeah, okay.
Absolutely.
So the first thing that I would probably do is kill autovacuum process that is running. Now, before all of you cringe in the room, what I'm planning to do is kill that autovacuum, and then increase the cost limit and all those, or set those to 0, and let a manual vacuum go crazy, and try and finish that cleanup as soon as possible, right? This will help me reduce all that I/O bottleneck and all that buffer contention that I was seeing. And as you see in this graph, that kind of starts dropping down at the moment vacuum increases, the moment vacuum finishes. The next thing I would do is plan some long-term mitigation. So the first thing I would do is partition that monstrous table. So if you have an 8 terabyte table, partition that into smaller 100 GB chunks, so that vacuum can go and clean up each of these smaller tables. Instead of cleaning up a huge hall, if there are smaller rooms, different people can go and work in those rooms. Or if you divide this large room into small sections, different people can go and clean them up. That same concept applies to partitioning as well. Also, if a particular area or a particular table is being more used and volatile, only that particular partition gets vacuumed. Rest of 7.9 terabyte data doesn't need to be touched. That only 100 GB data needs to be vacuumed, which can finish in minutes, not hours. I'll also throttle vacuum during my peak hours. I don't want, for such a large table, if there is constant vacuum happening, I don't want it to go crazy and disturb my OLTP workload. So instead of using the cost limit, I'll add the delay parameter so that it adds some kind of delay to put some kind of brakes on auto vacuum. It's like cleaning the breakfast hall, the tables in the breakfast hall while people are still having their breakfast. That is going to give me the benefit of OLTP, but I'll also have an aggressive manual vacuum that will go and clean up and do the catch up for me, which runs every day at around midnight or 2 a.m. when my traffic is very low. Then, just to be sure I'm not missing anything, I'll set up an alarm on freeze age. A limit of 500 million is a good starting point. That gives you enough time before it hits 2 billion. So set up that alarm, and then I'm going to assume that I will still end up having some bloat, or I may get caught off guard at times, and bloat may still appear in my tables. So once a week or once a month or once a quarter, I'm going to keep checking the bloat ratio, and then depending on where they are, I'll decide either once a month or once a quarter I'll do PG repack to reclaim storage from those tables that might have 60% or 70% bloats.
Okay, so you've kind of talked about inheriting a mess or being getting caught off guard when it actually comes to bloat. So Samir, what's the one thing that you think that catches people off guard the most?
I think if you ask me for one thing, I'll say index bloats. Everybody watches out for table bloats, and it's relatively easy to find out because you can keep watching PGStat user tables. You get dead rows there, and you can find the ratio with the live rows, and you can figure out if you need to do the vacuum or not. But indexes get missed out sometimes, and they are a little bit easier to get bloated as well.
So how do you kind of detect and prevent it then?
Actually, the PGStat user tables, if they're constantly having, let's say, 10-20% of bloat, that also is a good indicator that your indexes might be bloated too. Aggressive auto vacuum is a good mitigation strategy. If you see that pattern, then tune your auto vacuum settings. And once in a while, you may still have to do that thing called reindex. instead of doing just reindex, use reindex concurrently so that you're not blocking any other online operations. The last thing I would do is improve the chances of having a hot update. Hot update is a bit specialized. It has a fast path as compared to normal update. And it is something that I recommend customers to achieve as much as possible. You have to make sure that your schema is aligned with your workload. You're not having indexes on those volatile columns that change very often. So that's going to help you achieve hot updates.
So, how do you actually go about, tuning your and looking out for the fill factor for, your tables with frequent updates?
Yeah, thanks for reminding me of that, because fill factor is another thing that is going to play an important role in making sure that you are able to get hot updates more often. Now, the problem with setting very aggressive fill factor is you can end up with some other kind of contention, and I think you have got a very nice story to explain that.
That's exactly the reason I actually asked. So this is a situation of a e-commerce customer that we actually had that had a high volume of transactions that were coming in to their orders table, processing roughly about 30 to 50,000 transactions per second, and that's during their peak time, right? So basically your typical Black Friday, your flash sales that are happening. And they basically started complaining that the database is slow during that peak time, queries are timing out, we're kind of losing orders.
So looking at this graph, it seems like that red section, there is a lot of lock, there is a lot of extend contention. What was going on there?
So this is kind of like something a bit silly. Someone actually had gone in and set a fill factor on this table of 65%, and thinking it'll actually go in and help with the updates.
Okay. So how do you mitigate or how do you fix that?
So this was primarily a kind of like an insert heavy table with a table of like 65. I mean like the a insert heavy workload rather. So having a fill factor of 65% didn't work. So what we did was during that event we actually ended up going in and doing a alter table and set a fill factor of 90%.
Okay. And you didn't know to do vacuum full?
So fill factor only affects new pages that are actually getting created. So with a insert heavy table actually that's constantly growing, it's actually better to just do it for the new pages, and then with that the new pages will actually start using that new fill factor, solving the extend lock problem immediately. And for your existing pages, they're kind of fine. They are written to already, and they're not causing an issue right now. So we kind of left it at that. Okay, now that we've actually talked about that, so we'll actually move on to and talk about partitioning. So Samir, is partitioning really optional at scale?
No, not really, not at the multi-terabyte scale. At that point, the question shouldn't be whether we should partition or not. The question should be, how do we partition? And Postgres offers 3 different approaches. You can either partition by range. That means you've got a continuous set, and you can divide them into equal parts, and you partition based on that. Or you can use hash partition, where you want to avoid situations of hot partition. It's great for tenet style or anywhere where you want to distribute writes across multiple partitions. Then list partition, where you have data that is categorized by state, city, status, or something else, and then you can have different partitions by that category or list.
Okay, and how do you know which one is better?
Partition key and the approach that you will use for partitioning, both of them will actually depend on your query patterns. So you need to know your query pattern and align your partitioning scheme and approach with that. If you are partitioning by date, but you query by customer ID, that's going to introduce a new problem with Postgres not using pruning. And I think you're going to talk about one of them in the later slides. So I'll save my time on that. And I'll just focus on just saying, just align your workload with the partitioning scheme you choose.
I see. So you're basically saying, choose your partition key based on your query, not how you think your data is going to be.
Exactly. If you get your partitioning wrong, things will be much more worse rather than you're solving any problem.
Cool. So, having discussed that, like, how many partitions is just too many then?
Good point. Good question. I've seen both kind of extremes. I've seen where you partition a 10 terabyte table into 4 partitions. So you end up with 2.5 terabytes. So vacuum, which was taking maybe a day, now it's taking 4 hours. You have not really solved anything in that case.
So really, so how many is too many then?
That's another interesting point. See, the query time will linearly grow as you add more and more partitions. So I've seen situations where a user had 15,000 partitions, and in their case, their planning time was a lot more as compared to the query execution time, because now optimizer has to plan looking at all these partitions and then execute the query, and that's the problem with having too many partitions.
So what's kind of like the sweet spot, say?
You want to have something that is big enough to be useful and small enough to be maintainable. So you want something like 10 to 100 GB of size for your partitions, and keep them in hundreds or maybe 1,000, but not in tens of thousands. And if needed, you can also use sub-partitions, by the way, yeah.
Awesome. So the next thing, Samir, does manual partition management work at scale as well?
No, not really, not in practice. I've actually seen more problems. I've seen outages because people who were supposed to add a partition for the next month forgot to do that, and the script failed, or they did not know, they thought they'll come back after coffee break and do that, and they got a ticket and they never did that. And in that case, what happened is the insert at the midnight at the end of the month started failing. So typically you want to automate everything, use pgpartman, pgcron. These are both great in terms of pre-creating the partitions and scheduling that.
So what about archival strategies then?
Yeah, that is also going to be very important so that you don't end up with too many partitions. If you're maintaining historical data, you can detach old partitions. You can move them to cold storage if you have multiple different volumes. The beauty of partitioning is that detaching the partition is instant. There is no update. There is no MVCC in there. And you can even keep the detached partitions around for compliance or to serve queries like, hey, give me last 6 months statements for my bank account. You don't need to have all of that data sitting in the live table. So that's great.
Cool. So the next question is basically, how do you know that your partitions are actually healthy?
One of the things you want to do is keep monitoring the size of partitions continuously. If you have skewed partitions or uneven size, that's a red flag. Let's say you're partitioning by date and January is 50 GB, whereas February is 500 GB. That tells you that there is some kind of skew, there is some mismatch there. Maybe a hot partition or data skew.
Okay, awesome. So Samir, what would you say is the number one partitioning mistake that we've actually seen?
It's what I talked about earlier, right? Where you don't have your queries aligned with partitioning scheme, and they are not part of your where clause, and then you don't use partition pruning in those cases.
And what if the queries use different keys?
So if you have got where clauses or different keys in your select statements, then what you want to do is get the top 10 queries, look at your top queries, and at least make sure 80% of your queries align with your partitioning scheme. So if 80% of your queries are filtered by order date, that makes a good candidate to be partition key. But if there is customer key or customer ID, then that makes a great candidate for a partition key.
Okay, awesome. So, and what about joins between partition tables?
You can use partition-wise join. It's a very powerful feature in Postgres. Without that, you will end up doing n cross m combination across partitions and struggle with that. But very few people know about that, and I have been surprised by that.
And how do you enable it then?
There are a couple of things. One is you need to enable the parameter in your parameter file called enable partition-wise join. You enable that. It is off by default because enabling it has a planning overhead, but at a terabyte scale where you have hundreds of partition both sides, that planning overhead is worth because you're going to save a lot more in terms of execution time. The next thing you want to make sure is both these tables that are part of the join query, they both are aligned well in terms of their partitioning scheme. If they're ordered by they're partitioned by order date, they both should match that.
Sorry, so
and have the same boundaries as well.
Okay, so sorry, what do you mean same boundaries then?
If let's say the ordered table is partitioned by month, and it is partitioned by start and end of the month, whereas order items is partitioned by week. That's not going to work great. So we need to make sure that they're both having same partition boundaries and partition type as well. Okay, Roneel. Now let's talk about some challenges we see in case of workloads and query tuning, especially when operating with multi-terabyte scale. Let's talk about partition pruning that we parked aside earlier during our discussion. So yeah, all yours.
So this is another case study we actually had with another e-commerce platform. They basically had a 15 terabyte orders table. So they actually partitioned by order date monthly, which ended up being roughly about 180 partitions, which kind of looked good on paper. But the queries were actually scanning the all those 180 partitions that were there each and every time a query ran. So with that, the performance insights metrics on our end basically started showing lightweight locks through the roof, and each query was basically querying locks on each of those 180 partitions, right? And at the concurrency of thousands of queries per second, this ended up causing the lock manager to become the bottleneck.
So why exactly did the pruning fail in that case?
So functions on the partition key, right? So basically, for example, if you actually have extract, date truncate, cast functions, any functions that's wrapping the partition column makes it opaque to the Postgres planner, right? So Postgres only sees the function call, not the range comparison that's actually there. So it can't map the results back to the partition boundaries that's there.
Well, developers love all these kind of functions and expressions in the where clause. This sounds like an easy trap somebody can walk into. Is this documented?
Actually, yeah. It is definitely documented. So, but I would say it's kind of easy to miss, and especially with things like ORMs, right? That actually kind of makes it worse. They generate, that extract calls because it's a clean way to actually do it from the application, but it needs kind of to be mapped on the database at the relational layer as well. And the planner kind of needs direct comparison against the partition key to actually prune. So which actually becomes the problem. Okay, this is another great story we actually had. Mission critical system where the transaction lookup, the kind of query that kind of runs thousands of times a second. It's basically, it could be your mobile app, your web portal, any customer service application, where everything depends on it. So one morning we actually get an escalation where the transaction lookups are basically taking roughly about 45 seconds, and they used to be instant. So, and this was actually for a bank out of Australia. And as you can imagine, so a query running for 45 seconds, basically means that the customers can't actually see their, bank balances, any of their transactions and all. So this is kind of like a high severity case.
Doesn't sound like a good way to start your day. What was going on there?
So yeah, exactly. So we kind of like jumped on the call. The first thing we see and we pull out is basically the query plan, and immediately we actually go in and see that. So it was basically, if you look at the bad plan, that's actually it was starting to do actually a hash join on a 2 billion row table rather. So this is basically the good plan that's actually showing up now. And it actually shows everything's efficient. It's actually using a nested loop rather, and using indexes to actually get the rows of data to us. And with that, when the issue actually started happening with the bad query, it was doing a hash join, as I said earlier, built on top of sequential scans, which ended up actually started doing sorting, which is a lot of I/O. In fact, it was doing roughly about 45 gigabytes of temporary tables. Right. So and first it was for basically reading the table, and then temporary tables for that sort operation as well.
So why did Planner choose to use a bad plan?
Actually, we can't say that the Postgres planner is actually broken here. It's kind of making the best decision based on the information it has, right? So if it actually had the wrong information in terms of bad statistics, that's what we was actually working on. So we kind of like on larger tables, you kind of need to pay that higher penalty for stale statistics as well.
And how do you fix these kind of situations?
So the immediate fix for us was we basically just went in and ran analyze on the table, and that's it. The statistics updated. The planner started seeing the real row counts, and it basically switched back and started using the nested loop joins that it was doing. Basically, 45 seconds came down to 50 or thereabouts milliseconds instantly. And having said that, that was kind of just the band-aid solution, though. The real or the permanent fix in that was basically setting thresholds at the table level to ensure that analyze was actually kicking in at a regular interval at a small enough change so that it was actually getting updated frequently. Now, with that, Samir, how many times have you kind of heard, like, can we just also run analytics on our production OLTP system as well?
Too many times, and it always goes down the same way.
So, walk us through on what do you think, like, what you've experienced?
So a complex analytical query comes in, it scans 500 million records on a really large table. It grabs locks or acquires buffer pin locks and evict pages from the shared buffer, and suddenly that lookup query on a static data table that used to take 2 milliseconds starts taking seconds because it has to contend for I/O, or it is doing additional I/O that it never needed to do earlier. Application server starts receiving timeout errors because users are not receiving the result back. So application server retries, and in order to do that, it retries the connection and retries the query as well. Now suddenly all the connections are exhausted, and application server has to make new connections. So that's the whole cycle of bringing down your application.
So isn't the fix to just add more memory to it?
You would think so, but it's not physically possible to add memory for a database that is 50 terabyte in size. So you can't cache everything. The real fix is separating your workload. Read replicas or use read replicas for the analytics purpose, or even better, use a dedicated analytic infrastructure. Now, let's talk about parallel query, particularly when we are talking about analytics workload. When does it help?
So as you just mentioned, like basically, mostly our analytical queries, queries that basically go in and scan through large amounts of data. So instead of we having one worker basically scanning through a 2 terabyte table or 200 gig index, you kind of get like 8 or 16 workers splitting that workload.
And any particular parameter tuning that I need to bear in mind using parallel queries?
That's a great question. So basically, kind of like some of the parameters that to think about is basically, don't set your max parallel workers per gather, too high on OLTP systems. Things like 16 parallel workers on one analytical instance basically can end up starving your transactional workload. This is kind of another reason to actually separate your OLTP and analytics. So don't go too aggressive also on parallel tuple cost and parallel setup cost parameters as well. So very small values can actually force the parallel query even when it doesn't make too much sense.
Okay.
Now with that, what we see actually here is a lock weight manager contention. So Samir, in experience, what typically causes it?
Yeah. So let's imagine a scenario. You have got a 4 terabyte table with hundreds of columns, 120 columns. 20 of these are indexed, so there are 20 indexes in your setup. All these indexes were added over a period of time to support those ad hoc queries in the application or the dashboard inquiries, and those are working fine, but now suddenly every query starts adding the logging pressure.
So you're saying every query. So how does a simple query or simple select query cause a lock exclusion then?
Right. So what happens in Postgres is every select is going to acquire an access share lock on the table. It will also acquire an access share lock on the indexes it might end up using. And in this case, the number of those indexes is 20. So you got 20 plus locks just for one query. Now multiply that by the number of connections you have got. Let's say you have 1,000 connections or maybe 5,000 connections trying to do the same kind of lookup. Very simple, straightforward query. But because of the number of indexes, your lock manager is now struggling to keep up with all the locks being granted.
So what you're basically saying is more indexes means more contention.
Exactly. If particularly your indexes are above 16, that is kind of a sweet spot, after which Postgres will stop using fast path locks. And that's where the locking overhead will cause a problem. If you're interested, take a look at that blog that is from GitLab. They've talked about this topic in a lot more detail that we can cover in this presentation today. So basically, too many indexes are going to add an overhead on the locking infrastructure as well, not just additional storage or write penalty.
Awesome. So let's actually go in and talk about how I/O can also become a bottleneck, but particularly in inherent durability guarantees that actually come in with a relational database.
Yeah. So here are some basic things about storage and IOPS. In case of PostgreSQL, there are two different kind of IOs happening. One is on every commit, Postgres is writing to the vol files, transaction logs, and on every checkpoint, it's synchronizing or flushing the data files. Ideally, what you want to do is use separate storage for both of them. Use SSD, provisioned IOPS. You want sub-millisecond latency on these storages. Now, Roneel, do you want to talk about this particular customer's anecdote where we saw they were trying to save cost, which they were able to do for a month or two, I guess, but then they ended up paying a much bigger penalty because of storage?
Yes. So we actually had this situation where their customer basically started, they kind of picked the cheapest storage tier to actually save money, minimum IOPS, the smallest volume size that would actually fit their data. And this kind of looked great at that moment.
And what went wrong after that then?
So what really happened was from kind of the second month, checkpoints started taking like 10 minutes. And month 3, we started having things like latency spikes every 5 to 10 minutes, which was like clockwork. And that basically was your checkpoint intervals as well. And the storage just wasn't provisioned for the sustained write throughput of the multi-terabyte Postgres instances that they had.
So did they end up scaling up or adding more IOPS?
So yes, they actually ended up right sizing the storage with proper IOPS, proper throughput, and they basically also got high availability and durability as part of the package as well. And and with that, the latency also dropped. Checkpoints kind of became invisible as well, and they kind of have had the peace of mind on reliability. And month 5, I guess the only regret was not doing it from day one.
Yeah.
Now the next thing is basically on well generation. So well generation is something that's we see that teams go in and underestimate at scale quite often.
So vol files are 16 MB, right? How bad can it get?
So on a busy system that generates like gigabytes of well per hour, right? That's basically causing your network bandwidth to replicas, your disk I/O on the primary, and archival storage as well. So it actually kind of starts to add up very fast.
And what can you do about it?
Well, the easiest thing to actually do is basically do well compression on the first lever, right? So this goes in and reduces your well size with some CPU overhead, of course. You can also go in and look at your checkpoint timeout as well as your max well size. This control how often the checkpoints are actually happening on the database. And longer intervals also kind of mean that your checkpoint I/O storm is more sustained, but more well to replay in the case of a crash recovery. So it's kind of a trade-off between your performance and uptime. Now let's actually look at replication and how it can actually cause challenges at scale. So we have a situation here where the primary is kind of happily writing roughly about 50,000 transactions per second. So in this situation, Samir, what can you talk about like the scenario here and why the replica was struggling?
Well, the replica was struggling primarily because of single-threaded vol replay. It cannot keep up, practically cannot keep up with the write volume. And it is it's trying to replicate all these and do all these write operations while also struggling with the read workload that is contending for IOPS and buffer. So that's the basic practical challenge with read replica on a heavy write workload.
So how do we actually fix it?
Well, there are a few things that you need to do. There is no one silver bullet. First thing, tune the recovery settings. Use faster storage on the replica. Don't use substandard storage or scale down IOPS on read replicas because you think I'm okay with reads not being reads being slow because it's also affecting the writes that are replicated. Or architect around it by using cascaded replicas so that you can spread the load. Now, we have talked about storage, workload, and a lot of other scaling challenges. Now, we're going to very quickly go and look at some of the administrative tasks that are that becomes painful.
So we are referring to basically a situation where we actually had a customer go in and run a alter table. So even with kind of index creation and DDL changes on like a very large 5 terabyte table, the operations acquires a access exclusive lock, which kind of like end up blocking the database for several hours.
And how do you avoid that?
So some of the common things that we can actually go in and do, and as mentioned in the slide, we can actually go in and do create index concurrently, which without locking, add column with default in Postgres, add constraint with not valid. This kind of takes a brief lock with a node table scan, and then we basically go in and validate the constraint. So, but again, having said that, always ensure that you actually go in and test in a production clone.
What about upgrades for a large database?
These are basically like we actually have two identical environments. So blue is kind of like your current production, and then we actually have a green, which is a new version. So an example could be Postgres 14 is your blue, your target is Postgres 17.4, and you can just go in and build it and start replicating to it, validate, and once you're actually happy, you can actually go in and do the cutover.
Okay. Now, the other thing that is important in terms of administrative tasks is monitoring. Make sure that you are watching out for locks. You have got a track of replication lag, vacuum progress, replication slots. Make sure that we have been showing performance insights graphs here, but you can also build similar monitoring on top of wait events by looking at sessions and their wait events and aggregating them. Watch out for XID wraparound, H, long-running transactions. Look at for checkpoints, how often are they happening, how long are they taking typically, buffer cache hit ratio. These are some important metrics to look at. And then make sure that you're not just adding alarms. These alarms are actionable. So every alarm that doesn't have a mitigation approach is useless. Make sure that if you're sending an alarm that replication lag is more than 5 minutes, it has a related checkbook, so somebody can go and follow that checklist and mitigate that problem. Do you want to talk about the tuning very quickly?
So yeah, so some of the best practices for tuning that we've actually experienced and will probably suggest is ensure you set your shared buffers to roughly about 25% of the available memory. Effective cache size, 50 to 75% is kind of the sweet spot that we'll actually have. For workmem, this is important because this is a per operation memory. So ensure you start low and increase it for your specific queries that you're kind of spilling to disk. And your maintenance workmem as well, set it higher for vacuum and index rebuild operations as well. And also things like max connections, ensure you keep it as low as possible because you can go in and use a connection pooler. And connection management is important because with each connection, it actually comes with the memory overhead. So 500 idle connections waste gigabytes of memory as well. So things like PG bounce, or you can use RDS proxy in AWS in front of to ensure that max connections is what you actually need.
And then for backup, I guess you can't use PG dump anymore. You will have to use some kind of physical backup and plan for incremental backup so that you're not taking a 10 terabyte backup every night. And also keep testing your restores so that you know what your RTO is going to be like. If you're not testing your backups, then that's basically just taking backups and hoping they will work fine. All right, let's just quickly wrap up what are the common pitfalls that we have talked about throughout this presentation.
So things like ignoring vacuum until it's too late, not monitoring for replication slots, underestimating your schema change duration. That is basically your alter table that you've tested. For example, on a 1 gigabyte table, it's not going to scale too well on a 5 terabyte one now as well.
Anything else you want to talk about?
Yeah, so we also talked about running analytics on production systems as well, without separation, not testing upgrades thoroughly as well. And that's a classic, it kind of worked fine on a 100 gig database. And then when you're actually running a production upgrade, it basically is failing. So these are things to ensure that you're testing and are comfortable with.
Now let's try to wrap up all the learnings and lessons we have talked about. Plan for scale from day one. Partitioning strategy is critical. Don't try and retrofit that into a 10 terabyte table. You want to think about that right when your table is at 500 GB or 200 GB mark, and monitor everything, set up alarms, and have a proper mitigation and run books related to those alarms. Document your decisions, make sure that you're documenting every change, and you can walk back up from those changes if needed in future.
With that, thank you very much for joining us today. We hope these lessons from our real customer experiences help you.